White dwarfs are thought to be remnants of small stars which do not undergo supernova explosions. They shed their outer layers, and what is left behind is the core. They are no longer powered by any fusion reaction and are thought to cool very slowly over billions of years. In the past, astronomers have spotted white dwarf stars whose age would put them beyond the recognised timescale of our universe. Now, in a recent study, astronomers believe that these impossible stars may actually be more common than they thought. What is going on with these stars, and is there a different way to look at this which makes more sense? As it is believed that the core of a star is what forms the white dwarf star, the mass of the white dwarf is therefore directly related to the original star. Theory suggests that very slowly its mass will decrease, therefore the mass is directly related to the original star, which in turn must reflect its age. So by measuring the mass of a white dwarf star, they can determine its age. Over the last 10 years, astronomers have discovered over 100 white dwarf stars with masses so low they appear to be older than the universe itself. Most of these 100 stars actually have a companion. So the first thought astronomers have is that potentially the companion star must have pulled material away from the white dwarf star. The problem is that there are some of these white dwarf stars that have no companion star at all. In research recently published, astronomers have discovered a new white dwarf star with extremely low mass that does have a companion star. The problem is that this companion star is too far away to be able to siphon off any material. Also, the odds of finding such a pair is so low, it means that these types of white dwarf stars may be far more common than previously imagined. The white dwarf they discovered is only about 1/5 the mass of our Sun. Desperate to try and explain this, they point out that it is possible that this white dwarf is not a white dwarf at all. Here it is important to understand that the telescopes we use to measure these systems do not show crisp, clear images. They are blurry and open to interpretation. They suggest that it might be possible that the white dwarf is instead either a black hole or a neutron star. The problem with this concept is that white dwarfs are the most common companion stars that we see, not neutron stars and not black holes. Secondly, they would need to explain how such a low-mass black hole or neutron star could form. Small versions of these have so far never been observed. The lead astronomer states, "I admit that this argument might not be totally convincing given that we don't have a good explanation for how this white dwarf was formed anyway. Single-star evolution cannot explain such a low-mass white dwarf, so it's been assumed that the interaction with a close binary plays an important role. But again, this binary interaction scenario fails to explain the observed orbit of the KIC 8145411 system, because the orbit is not so close as required for this scenario to work. So some part of this story needs to be modified, although we don't yet know which." Now this is a beautifully honest assessment of their predicament, and I particularly like that he used the word story. So is there a different way to look at this which makes more sense? Yes, again, if we consider that stars are not the huge balls of gas powered by fusion at the core, but are instead powered electrically. Stars with a lower input current would be dimmer and put out less overall radiation. Of particular interest is the fact that the majority are found with companions. Again, this is not entirely surprising if we consider that some electrical stressing event causes the original star to fission, splitting in two. Let's imagine that this split was not even, so we end up with a larger and a smaller star. The larger one would continue to get the majority of the power, while the smaller one would get a much smaller amount, making it appear like a white dwarf. So how would we explain white dwarfs with no companion star at all? In this case, these could be stars which potentially have been ejected from the main star filament or end up somewhere with a much lower current density, causing a great reduction in the output, again making it appear like a white dwarf. And again, in these scenarios, the mass of the star is not so important. because there isn't a critical limit at which they form. It is all to do with the current that comes into it. So far, we have not been observing stars for long enough to really know what they are or how they change over time. In the mainstream model, no one actually knows if they really do lose mass over time or not. It would be foolish to assume that the electric universe had all the answers mapped out, when we do not even have a consensus on what the model for the Sun actually should be. We have Alvan's solar circuit with a fusion star, we have Jürgen's electric sun model, Don Scott's adaptation of this model, a cathode sun model, a plasmoid sun model, and now also robotized sun model as well. Each has its merits and each has its flaws. No one model is currently able to describe all of the observations that we see from the Sun. This is a topic that I want to come back to in the near future, as more work needs to be done here to move these models forward. As always, be brave, be curious, the truth is waiting for us. Until next time.